All right, hello again. So in this video, we're going to think about how to take the intuition of an interior solution like this one, right, where we have an optimal choice, where everything better is unattainable, right, is too expensive, everything else that's feasible is worse. We're going to think about how to calculate this given a particular set of preferences and a particular budget. So the first thing I want to do is I want us to notice two properties that have to be true of an optimal choice like this, that we're going to use to calculate this point. So the first property is pretty straightforward. It's that we use our whole budget. Right? In other words, we can't have an optimal choice like this, because as long as more is better, we'd be better off, right, having more of one good or the other. The second property is a little harder to see, and it's that the slope of our indifference curve has to be equal to the slope of our budget constraint. Slope of indifference curve equals slope of budget constraint. Let's think for a minute about why this has to be true. Essentially, the reason is we need our indifference curve to only touch our budget constraint at one point, and in an interior solution, it's touching our budget constraint somewhere in the middle. So if the slope was steeper, it would have to cross, right? And then we would have some overlap over what's better and what's feasible. And if the slope was less steep, it would have to cross there too, right? The only way for us to have our indifference curve touch our budget constraint but not cross it is for those slopes to be equal. Okay. So what does this mean? To think about this, let's use particular budget constraint, particular preferences. So for the budget constraint, we'll just stick with what we've been doing. We'll just say 1/2 times f plus 2 times t less than or equal to 12. And for the indifference curve, or for the utility function, let's mix things up a little bit, try something new. Let's say that our utility of froyo and toppings is going to be given by 2 times the natural log of f plus the natural log of t. All right? Cool. So how do we turn these two rules here into a procedure for solving for the optimal choice, given this budget constraint, given these preferences? So for rule 1, it's going to be very, very simple. All it means that we use our whole budget is that we turn an inequality here into an equality, right? We have to spend exactly $12. So for rule 1, we'll just say 1/2 f plus 2t has to equal 12. So far, so good. But how about rule 2? How about the fact that our slopes have to be equal? What's that going to look like? Why does that have to be true? What does that mean? Well, to think about this, let's remember what these slopes are and what these slopes mean. So what's the slope of our budget constraint? So as we talked about, right, our slope of our budget constraint is going to be the price ratio. It's going to be PF over PT. And what does that represent? What it represents, what it means, is the cost, right, how much topping we have to give up to get an extra ounce of froyo. How much topping have to give for froyo, right? Okay. So now how about the slope of our indifference curve? Right, so this slope here is PF over PT, the amount of topping we have to give. So if you remember from last lecture, the slope of our indifference curve has a special name, right? We call it the marginal rate of substitution. MRS, T for F. And it's going to equal the ratio of the partial utility with respect to F, right, the marginal utility of an extra byte of froyo, versus the partial utility with respect to T, the marginal utility of an extra byte of topping. So it's going to be du df over du dt. And what was the meaning of this? What was the meaning of our marginal rate of substitution? The meaning was, right, how much topping we're willing to give up for an extra byte of froyo. Right, that's why it's bendy like this, right? We're willing to give up more topping when we have a lot. We're willing to give up less topping when we have a little. So how much T we're willing to give for a byte of froyo, right? So how much we have to give versus how much we're willing to give. And so when these are equal, when our marginal rate of substitution equals the price ratio, that means that we're willing to give up exactly as much topping to get an extra byte of froyo as we have to. And if that wasn't true, right, if we're willing to give up more topping to get a byte of froyo, that would mean the marginal rate of substitution was steeper than the budget constraint. And that would mean we should do it, right? If we're willing to give more topping than we have to get froyo, we should give up some topping, we should get some froyo, right? We would have an indifference curve that looks like this, and we want to move this way. And if we're willing to give up less topping than we have to get some froyo, right, then we've got too much froyo and then not enough topping. But if we're willing to give up less topping than we need to, then we shouldn't do it. We should do the opposite, right? We have a marginal rate of substitution that's less steep than our price ratio, and we should move that way, right? We should give up some froyo and get some topping. If they're equal, we can't make ourselves happier either way, either by giving froyo for topping or giving topping for froyo. Okay, great. So now we're getting pretty close to figuring out how to solve this, right? I'm just going to take this, and then I'm going to come up with a procedure to find out when both of these rules are true, right? Solving our budget equation with equality, setting our marginal rate of substitution equal to the price ratio, right? So our second rule, our slope of our indifference curve equals our slope of our budget constraint. What this means is that our marginal rate of substitution has to equal our price ratio. Okay, so how do we solve this thing? Let's do some math. Step one, we want to find our marginal rate of substitution. We do that, right, by taking these partial derivatives. So we'll say du df is going to equal the derivative of our utility function with respect to f. So what is that? Well, remember, when we're taking the partial derivative, we treat f as a variable, we treat t as a constant. So this is 2 times the natural log of f plus the natural log of 4, right? So this part doesn't matter at all for the partial derivative, it's just this part. What's the derivative of the natural log of f with respect to f? It's 1 over f, right? So this is going to be 2 over f. And what's du dt? Same thing, right? Treat f as a constant, so this is just some constant plus the natural log of t, so it's 1 over t. And our MRS is going to be 2 over f divided by 1 over t. So our MRS is going to equal, right? We can basically multiply the top and the bottom by t, and we can get 2 times t over f. Let's take a minute to make sure this makes sense. So if we have more topping, our MRS goes up. The more topping we have, the more willing we are to give it up. That makes sense. If we have more froyo, our MRS goes down, right? If we've got more froyo, we're less willing to give topping to get froyo. That also makes sense. Great. So we're off to a good start. Now that we have our MRS, we set it equal to our price ratio. MRS equals price ratio. So we say 2 times T over F is going to equal PF over PT, which in this case happens to be 1/2 over 2, right? Equals 1/4. So 2 times T over F equals 1/4. We can solve for T and say T is going to equal 1/8 times F. Awesome. So now what we've done is we've said in order for us to have an MRS with the same slope as our budget constraint, right, we're going to have to consume 1/8 as much topping as we do froyo. Step 3, so we're going to plug this into our budget constraint. Right? So now we know the ratio we need to consume them in, but we don't know how much we can afford. The way that we find that out is we use this equation here, right, our budget constraint. So we're going to say 1/2 F plus 2T equals 12. We know that T equals 1/8 F. So this is going to be 1/2 F plus 2 times 1/8 F equals 12, right? 1/2 F plus 3/4 F equals 12, or I'm sorry, 1/4 F equals 12, right? F is going to equal 12 times 4/3, which is going to be, right, 12 divided by 3 is 4, so this is going to be 16. Great, so now we know how much froyo. What do we do to get toppings? We're going to use this rule again. So we know F equals 16. We know that T equals 1/8 times F. So T is going to equal 1/8 times 16, which equals 2. So our final answer, F equals 16, T equals 2. Right? And why does this work? Why is this our answer? Because we know that we're consuming a ratio where we wouldn't want to give up one for another, and we're consuming our whole budget. So we're starting with these 2 properties of our graph, right? We're using them to calculate our optimal solution. All right, fantastic. In the next video, we're going to talk about how to solve corner solutions. So solutions where instead of having an optimal point where we consume some of each, we have an optimal point where we either only consume froyo or only consume top.